Choosing the right mobile phase pH is one of the most critical steps in SEC method development. We call it the invisible protein because in a perfect SEC run, the protein should pass through the column without the chemical surface ever seeing it. Next, we'll explore how to use pH to achieve this perfect size-only separation. In most chromatography, binding is the goal, but in SEC, invisibility is the goal. For a true size-based separation, the protein must only go through physical pores, never interact with the surface chemistry. Any electrostatic interaction between the protein and the resin will ruin your data. It's a common mistake to assume SEC columns are perfectly neutral. In reality, even high-quality silica columns have a slight negative surface charge due to residual silanol groups. If your protein is positively charged, the column acts like a magnet, trapping your sample and destroying the run. To fix this, we have to look at the relationship between the mobile phase pH and the protein's isoelectric point, or pI. If pH is less than pI, the protein is positive and sticks to the column, causing late elution. If pH is greater than pI, it becomes negative and is repelled, eluting early. On paper, if you match the pH exactly to the pI, the protein has a net zero charge and shouldn't interact with the column at all. This theoretically creates a perfect, neutral size-based separation. However, this leads to a dangerous textbook paradox. While a net zero charge eliminates column interaction, proteins are actually at their least soluble at their pI. If you run at pH equals pI, your protein will likely aggregate and precipitate, which can physically destroy your expensive column. Our first rule is to always prioritize solubility first, because a precipitated protein is useless for analysis. You should always set your mobile phase pH about 1.0 to 2.0 units away from a protein's pI to keep it in a safe zone. The trade-off is that the protein now carries a charge, meaning it might interact with the column again. To fix the charge issue created by rule number 1, we use rule number 2, deploy the salt shield. Since we can't use a neutral pH, we add 150 to 300 millimeters of sodium chloride to muffle those electrostatic charges. These salt ions act as an invisibility cloak, blinding the column to the protein's charge while keeping it soluble. Sometimes you'll deal with extreme proteins. For highly acidic proteins with low pI, the repulsion is so strong you might need to drop the pH to 6.0 to reduce that negative charge. For very basic proteins with high pI, the attraction is intense, so you must crank up the salt shield over 200 millimeters to keep them from sticking. In the biotech industry, the vast majority of therapeutic proteins are monoclonal antibodies, or mAbs, because they contain a high proportion of basic amino acids like lysine and arginine. They have uniquely high pI, usually between 7.0 and 9.0. This means that under standard lab conditions, these life-saving drugs are almost always positively charged. If you look at 100 different SEC methods for mAbs in industry, about 80% of them use an exact pH of 6.8. This isn't a coincidence. It is an engineered sweet spot based on 3 non-negotiable technical realities we are about to cover. First, we use phosphate buffers because they have incredibly low UV interference. However, buffers only work effectively within 1 unit of their pK, and phosphate's pK is 7.21. A pH of 6.8 maximizes that buffering capacity while keeping the environment safely on the slightly acidic side. Second, pH 6.8 perfectly threads a needle between stability and stickiness. If the pH is too low, for example pH 5.0, the mAb becomes too positive and binds the silica. If it's too high, for example pH 8.5, it hits the pI and aggregates. pH 6.8 keeps it soluble without overwhelming the salt shield. Finally, we have to protect the hardware. High-resolution silica columns are very expensive, and silica physically begins to dissolve and degrade at a pH above 7.5. By capping your mobile phase at 6.8, you ensure your method is rugged enough for hundreds of consecutive injections. If you are asked to develop an SEC method for a new biological tomorrow, here's your universal phase 1 blueprint. Start with 100 millimeters potassium phosphate as your engine. We prefer potassium over sodium here to prevent any precipitation during cold storage. Use 150 to 200 millimeters sodium chloride as your invisibility cloak and set your magic number to pH 6.8. This is the absolute best starting point for developing a professional SEC method. To wrap up, here is the method developer's checklist to bridge the gap between theory and industry reality. First, prioritize solubility by staying 1.0 to 2.0 units away from the PI to avoid aggregation. Second, muffle electrostatic charges with salt rather than forcing extreme pH shifts. Third, always anchor modern MAB methods at the 100 millimeters phosphate, 150 millimeters sodium chloride, pH 6.8 standard. Follow these rules, and you are officially ready for the lab.